A very good morning, class 12th. Moving on further to the second part of the P block of elements, unit 7, halogens, class 12th NCERT. We are doing halogens, that is your group number 17. This is the second part of the video. In this part, I would be taking up the hydrides, ionic character of the halides, oxyacids and interhalogen compounds. Fine. So let's begin with the class. Now, when we talk about hydrides, our interest is in this bond, and you very well know this is a small sized atom while this is comparatively larger. So, as your halogen goes from fluorine to chlorine to bromine to iodine, the bond length will increase because of the difference in the sizes. If the bond length increases, then the bond strength will decrease. That is point number 1. Secondly, this is a bond where the shared pair of electron would be more towards halogen. If the shared pair is more towards halogen, therefore there is a delta negative and a delta positive. So, this is a polar bond, which also means there will be a dipole moment. Now, you very well know the dipole moment is represented from the positive center towards the more electronegative center. This is how we represent the dipole moment in all the hydrides of group 17. Dipole moment is denoted as mu, and it is the product of charge into distance. Out of these two parameters, it is the charge which is predominant. So, the size is not predominant, it is the charge which is predominant. Therefore, when we talk about the dipole moment, because fluorine is most electronegative, so the dipole moment would be in this order, because the charge separation would be more in case of HF due to the highest electronegativity of fluorine. Moving on to next bond, if we talk about the bond length, as already done, the bond length would be higher as the size of the halogen goes on increasing. So, this is the longest bond length. Now, since it is the longest bond length, so when we talk about the bond strength, if we talk about the bond strength, then the order automatically becomes the reverse, because bond strength will be more if the overlapping is better. So, Hi has the weakest of the bonds out of the hydrides. Is that okay? Moving on further. As I just said that Hi has the weakest of the bonds, since this bond is the weakest, therefore, if you talk about the Hi bond, this bond becomes weak and it can be easily cleaved. And if it is cleaved, the shared pair of electron will definitely move towards iodine and your H positive would be liberated. Hence, hydrides become acidic in nature. So, if you are asked about the acidity, it is the bond length which is important, and acidity is directly proportional to bond length, because the weaker the bond, easier the liberation of H positive. Therefore, when you talk about acidity, the order would be this. The same question could be, they can ask you what is the value of Ka, or they can even ask you as the bond dissociation energy. Now, which is the strongest bond? HF. So, it would be difficult to break this bond. Hence, the bond dissociation energy would be highest in case of Hi and the lowest in case of HF and lowest in case of Hi. On top of it, there are sometimes they asked you as thermal stability. Now, what does this mean? Thermally it is stable. If you heat it, the bond does not break. Thermal stability is again directly proportional to your bond strength. Stronger the bond, more stable it will be to heat. Hence, the thermal stability order would again be like this. Any problems? Moving on to the last property, which is your boiling point. Now this boiling point is directly proportional to intermolecular force of attraction. Now in the hydrides, as you very well know, the intermolecular, since the hydrides are polar, therefore the intermolecular force of attraction has to be dipole moment. Now on that basis, your HCl has a higher dipole than HBr, higher dipole than HI as already discussed. So the boiling point order should be this. But the problem lies with HF. In case of HF, the boiling point order should be like this. But the issue here is this is not so. The intermolecular force of attraction dipole moment is common to all of them because all halogens are electronegative. In such cases, it is the size parameter which is more predominant. Whenever we talk about a group, it becomes the size which becomes more predominant. Therefore, when we talk about intermolecular force of attraction and the boiling points, we talk about the London force which is more predominant in this case. Hence, the boiling point therefore always increases down the group. So the boiling point order actually is this. But the surprise factor is that for HF, the boiling point becomes the highest. Why so? The reason is, in case of these, we talk about London force. But when we are at HF, we talk about hydrogen bonding. We have a strongest hydrogen bonding between HF molecules. Therefore, the intermolecular force of attraction in case of HF is hydrogen bonding. Hence, the order of boiling point becomes this, where HF has the highest boiling point of all. Please do not be confused. Do not take dipole moment when we talk about the boiling point. You have to take the London force always and hydrogen bonding for the first member. So, this becomes exceptional. Is that fine? I would just illustrate the hydrogen bonding for you. When you have HF molecules in vicinity of each other, it is found that the shared pair of electron is more towards fluorine. Hence, there is polarity developed like this. Now, this H positive gets attracted towards the electronegative atom of the other molecule, and this is what is known as hydrogen bonding. Whenever the electropositive hydrogen in a polar covalent bond gets attracted towards the electronegative center of the adjacent molecule or a molecule nearby, this leads to attraction called as the intermolecular hydrogen bonding, and this is the reason it is directly related to your boiling point. Also, it is directly related to your physical state, and that's the reason HF is the most viscous acid. What does viscous mean? Thick, like honey. It's thick and viscous because the molecules of HF are pulled closer to one another, so it has a high density. It's a high density liquid, which is what I mean when we say it is a viscous liquid. Let's now talk about the ionic character of halides. Now, supposing I have a sodium fluoride, a potassium fluoride and a rubidium fluoride. Out of these three, in these three we have a metal and a non-metal. The electron is transferred from the metal to the non-metal, electron is transferred from the metal to the non-metal, and so on. Out of these, since fluorine is common, so the pulling part is common. In which case do you think will the transfer of electron be fastest and maximum? The transfer of electron will be easiest in case of rubidium. Why? Because rubidium is largest in size. Since it is largest in size, therefore ionization energy is low, so the electron transfer is easy. So the ionic character of the bond is going to be like this. Let me take a second example. If I have a magnesium fluoride, I have a magnesium chloride, and I have a magnesium bromide. Now what? Now under these circumstances, as you can see, all the three metals are same. So the donating capacity remains the same. It is the pulling capacity which is more in case of fluorine, less in case of chlorine, and least in case of bromine, because fluorine is most electronegative. So the electron transfer is maximum in MgF2. Therefore, this becomes most ionic. So the ionic character now would be like this. Fine. Moving on to the third example. If you have tin dichloride and you have a tin tetrachloride, now the metal and the non-metal both are same. Now you need to know something about Fajan's rules. If you have no clue about Fajan's rules, please watch my video in the channel for class 11th chemical bonding chapter unit 4. You would come across Fajan's rule, or else you can type Fajan's rule by Seema Makhijani and you can reach this particular video. Now according to Fajan's rule, covalent character is higher if positive charge on the metal is higher. Now out of these two, in this case tin has a +4 oxidation state, while in this case tin has a +2 oxidation state. So whenever there is a higher positive charge, this becomes more covalent. So this is more ionic. Is that fine? We can also take one more example under this category. Supposing I have NaCl, MgCl2 and AlCl3. Now out of these three, we very well know sodium, magnesium and aluminium are across a period and the size decreases across a period. So the smallest is aluminium. So electron transfer from aluminium to Cl is going to be difficult. This, out of these three, this is the largest metal. Therefore, ionization energy would be low. Therefore, electron transfer is going to be easy. Hence, this becomes most ionic, so on and so forth. Fine. Moving on further to the oxoacids or oxyacids. Now, oxoacids or oxyacids are for a non-metal. This is your non-metal. The non-metal should have one double bond O and one OH. Rest it can have anything. These are the compulsory things that it may require. Apart from this, it may have anything, but this is the condition for a oxoacid to exist. So when we talk about halogen, our general formula for halogen will become something like this. Fine. Under the oxoacids, we have categories. We have oxoacids of these types: HOX, HXO2, HXO3, HXO4. Let's find the oxidation number of halogen in each one of them. The oxidation number here is +1. Calculate please, it's +3. Please calculate, it's +5. This is +7. Now according to IUPAC, the names given to these acids are halic 1 acid. This is also halic 3 acid. This is called halic 5 acid because of the oxidation number of halogen. So what will you call this? Halic 7 acid. But the common names is what you should know, because common names are the ones which you will require for the question answers. The common names of them are, this is called as hypohalous acid. When you have HOX, it is hypohalous. This is called as halous acid, HXO2. HXO3 is called as halic acid, and HXO4 is called as perhalic acid. Now, if I ask you to give me the formula for, let's say I ask you to give me the formula for bromic acid, what would you write? Which is bromic? Halic acid. So HBRO3 should be your answer. If I ask you to give me the formula for chlorous acid, what will you write? That is HClO2. If I say I need periodic acid, so in that case the formula would be HiO4. Clear? So you can write the formula for any one of them. Now let us talk about the other properties of these the oxyacids. When I talk about these oxyacids of chlorine, I find the formulas are HOCl, HClO2 for chloric acid, then you have HClO3 and you have HClO4. All the four of them will exist. But when I talk about chlorine, HOF, HFO2, HFO3, HFO4, you should know this, that none of these three would exist. The reason being, here fluorine gets an oxidation state of +3, +5 and +7 as already done in the part 1. Fluorine cannot show these oxidation states owing to absence of d orbitals. Fine. So only oxyacids of fluorine is HOF, that is hypofluorous acid. Now let us talk about the acidic character of the oxyacids. Now it is found that if you have an HOX, HXO2, HXO3 and HXO4, your property of acidic character is this: more the number of, higher the oxidation state. So acidic character is directly proportional to oxidation number of the halogen. Also, if you are asked which is the best oxidizing agent, so as an oxidizing agent also the order is the same. The reason is oxidizing agent is directly proportional to number of oxygens available or also the oxidation number of halogen. Is that okay? So if you are asked oxidizing agent, that's the order. If you are asked acidic character, that's the order. Now we come to the reason why do we have it like this. To understand the reason, you need to understand the bonding first. So these are the structures of HOCl, HClO2, HClO3 and HClO4. Here you have Cl using 3 electrons, so it is left with 2 lone pairs of course. Here it has used 1, 2, 3, 4, 5 electrons, so 1 lone pair, here nothing. Now why is this most acidic is the question mark. Why do we make this as the most acidic one, which means H positive is easily liberated from this. The reason is, let's say this loses an H positive. If it loses an H positive where oxygen pulls the electron and H positive is lost, what am I left with? I am left with a Cl, double bond O, double bond O, double bond O and an O minus. Now this is a perchlorate identity. Now this perchlorate is resonance stabilized. If this is the acid, then you very well know after removing the proton this becomes a conjugate base, and this conjugate base is stable due to resonance. Since it is stable due to resonance, which is can be understood as you have this goes here, this goes here, you can draw many resonating structures. Also this negative charge is shared all over by the 4 oxygens which are electronegative. So this is resonance stabilized. So conjugate base being more stable leads to easy loss of proton. So this becomes most acidic. Hence on the basis of this, if I remove this, in this case if the H positive is lost, what am I left with? I would be left with only this kind of identity. The resonating structures would be less in number because of 3 oxygens. If this is lost, then I would be, this loses a proton. What am I left with? A Cl, double bond O and an O minus. Now this identity again would be less resonance stabilized because of only 1 pi bond. This has maximum pi bonds, therefore more number of resonating structures, therefore more stable. Hence this becomes most acidic. This would have the highest Ka value and lowest pKa. For those of you who have no idea what do I mean by the term pKa, is minus log of Ka. तो जौन से एसिड का Ka is higher, the pKa should be lower. So highest Ka would always have a lowest pKa, because pKa means minus log of Ka. Moving on to the final topic, which is the interhalogen compounds. The interhalogen compounds, as the word says, refers to the compounds in which you have different types of halogens bonded to each other. The general formula by which we represent this is one halogen and the other halogen n times. As you can see, I have deliberately taken one capital X and one small x. Here the small x refers to a smaller halogen and capital X refers to a larger halogen. N can be 1, 3, 5, 7 on the basis of oxidation numbers, which we have already discussed, that halogens can show these oxidation numbers. So the interhalogen compounds are like this, and the X is a smaller or the more electronegative halogen, which means if I write ClF3, this is okay, but if I say it should be something like Br and I3, then this would be wrong, because more number is for the more electronegative atom. Fine. Also in the compounds of this capital X can never be fluorine. This should be understood, because capital X cannot be fluorine, because fluorine can only form one bond. Why? Due to absence of d orbital. So your capital X can never be fluorine. You cannot have more number of such compounds. This larger halogen, or this is the less electronegative halogen. Is that fine? I hope that's clear. So you can have compounds of the type BRF5, you can have IF7 and so on. Now let's say I have interhalogen compounds ClF. How do you think will it react with water? Now water has two identities in it, H positive and OH minus. And your interhalogen compound also has a negative identity and a positive identity. Therefore, you should understand that the compound in this case formed would be this. Your H positive will bind to F minus and your OH would go to Cl. So the compound formation has to be understood. Is that okay? The more electronegative interhalogen compound may, whatever is the more electronegative, will grab the H positive of water. This is how the reaction takes place. Moving on further, let's talk about the structures and geometries. Now these of structures and geometries of interhalogen compounds, I will do a few of them to get a grasp of the topic. We are doing the VSEPR theory. Let's do the first, BRF3. Now the central atom is bromine. The central atom bromine has how many electrons? 7 electrons. Out of these 7 electrons you have used 3. So 3 are bond pairs and you have not used 4. So 2 are lone pairs. So you have to adjust 5 things around the bromine atom. So for 5 things the geometry has to be trigonal bipyramidal. In this geometry you have to place 2 lone pairs, and the advice is lone pairs cause maximum repulsion. So the lone pairs should be on the equatorial side. So you have 2 lone pairs, I place the lone pairs here and your fluorines come here. So the geometry is T-shaped. The shape is T-shaped and the geometry is asked, it is trigonal bipyramidal. Is that fine? Let me take the second example, ClF5. This is your central atom. It has 7 electrons, out of which you have used 5. So 5 are bond pairs. You have not used 2, so 1 is lone pair. So total is 6. So the geometry or the shape of the 6 positions is always octahedral, like this, one above, one below. All the angles are 90. So there is no issue. You can place your lone pair anywhere that you like. But the advice is try to place it either above or below. So I am placing the lone pair here and I am placing the fluorines on these positions. So if you are asked the geometry, it is octahedral, and if you are asked the shape, then you remove the lone pair. Without the lone pair, the geometry is square pyramidal. Fine. The last example is IF7. This is the central atom with 7 electrons and all 7 are used, so it is 7 bond pairs. For 7 bond pairs, the geometry is pentagonal. 1, 2, 3, 4, 5. 5 bonds on this plane, 1 above and 1 below. Since there are no lone pairs and all fluorines are to be placed, so you do not need to give it a thought. Just place the fluorines. You should know this angle is 90 while these angles are 72. So this is your pentagonal bipyramidal geometry, and the shape both are same because there is no lone pair. Moving on to the tail end of the lecture, let's compare a pure halogen to an interhalogen compound. I have this Cl2 and a ClF. The first thing is the boiling point, which is directly proportional to intermolecular force of attraction. Here the force of attraction is London, while in this case it would be dipole moment. Therefore, out of the two, which has a higher boiling point? This, because you would have a delta minus and a delta positive. Moving to the next, out of these two, if I want to compare their reactivity. Now the reactivity is dependent on the weakness of the bond. Now here the size is different, so the overlapping will be not easy, not effective. So this bond is weaker. Since it is weaker, it will easily break. So this again becomes more reactive owing to the weaker bonding. And why is the bond weak? Because the sizes of the two atoms are different, so overlapping will be not effective. Coming to the third property, the dipole moment. When I talk about the dipole moment, here there is no dipole moment. The dipole moment here is 0. While this is a polar molecule because there is a difference in electronegativity. Lastly, ionic character. Here it is pure covalent, while this would be comparatively a polar molecule. So the ionic character is also higher for the interhalogen compounds. With this, I end my class on group 17. I have tried to cover up all the reasoning questions possible and the concepts involved. I hope you have liked the video. Please share it with your friends. Bless you kids. Do awesomely well in your life. Bye.